We discussed earlier that the translational motion of a rolling body depends on its rotational motion. Now, we are going to discuss in more detail the relationship between the kinematic quantities of translational and rotational motions. The first translational quantity that we are going to discuss is tangential speed. To explain this, imagine a disk, rotating at a constant angular speed, omega. This angular speed of a particle p, corresponds to a form of speed called tangential speed, or velocity, denoted by letter v. It is the distance d, traveled by a particle p, on a rigid body in a given time interval. This distance is equal to the arc length. We knew that the expression delta theta over delta t, is the constant angular speed of the disk, therefore the tangential speed v, is also expressed as the angular speed times the radius. Remember that when using this formula, the angular speed must be expressed in radians per second, so that the tangential velocity will be in meter per second, for as long as the unit of radius is in meter. This equation shows that, in order to transform angular speed into tangential speed, we simply multiply it with the distance r of the particle from the center of rotation. This is also similar if we are going to transform angular displacement into arc length. Later, we will see that it also applies with the transformation of angular acceleration into tangential acceleration. Remember that the orientation and direction of the tangential speed at a particular point on a rigid body is always tangent to the arc of the circular and depends entirely on the direction of its angular speed. Although the angular speed of any point on the rigid body is constant, the tangential speed varies with the distance of the point from the center. The point which is farther from the center of rotation has greater magnitude of tangential speed, since that point has traveled a longer arc length than those points closer from the center. In this figure, if the distance of point A is twice the distance of point B from the center, then when a disk rotates, the arc length traveled by point A is also twice the arc length traveled by point B. Therefore the tangential speed of point A is also twice the tangential speed of point B. We learned earlier that angular acceleration alpha describe the rate of change of angular speed of a rotating body. It is a quantity that can be used to describe whether a rotating body is speeding up or slowing down. A change in angular speed also corresponds to a change in tangential speed. The rate of change of tangential speed is called tangential acceleration, denoted by a sub tan. In terms of the initial and final tangential speeds, tangential acceleration is expressed as final tangential speed minus the initial tangential speed, over time interval. Now, we are going to determine the relationship of angular acceleration and tangential acceleration, by replacing tangential velocity by the product of angular speed and radius. From here, this expression is the angular acceleration, hence tangential acceleration is also given by the equation radius multiplied by the angular acceleration. This equation shows that, in order to transform angular acceleration into tangential acceleration, we simply multiply it with the distance r, of the particle from the center of rotation. The tangential acceleration of a rotating body only describes the change in magnitude of the tangential speed, not on its direction. We knew, from Unit 1, that in order to compel a particle from straight-line motion into circular or rotational motion, the direction of the speed of the body must change. This change in the direction of tangential velocity is called centripetal or radial acceleration, denoted by a sub c. Centripetal acceleration is always directed towards the center of rotation, and it is always in place even if the body rotates at constant speed. From Unit 1, centripetal acceleration is expressed as v squared, over r. But tangential speed v is also the product of angular speed omega, and the radius r. Therefore, centripetal acceleration is also given as the square of angular speed, multiplied by the radius r. When a rotating body speeds up or slows down, Any particle P experience both tangential and centripetal acceleration. The combination of these two types of acceleration is called total rotational acceleration. It is defined as the resultant acceleration of the tangential and centripetal accelerations. So we used Pythagorean theorem in order to calculate the total rotational acceleration. Let us give two sample problems. Problem number 5. A car moving at a constant velocity traveled 1,500 meters in 60 seconds. Letter A. What is the average velocity of the car? Letter B. If the diameter of each tire is 40 centimeters, determine its average angular speed, in RPM. Letter C. Determine the number of revolutions completed by each tire in this time interval. Assume that the tires do not skid. Let us analyze the problem. Imagine this is the car. So according to problem, it travels a distance d of 1,500 meters in a time of 60 seconds. The diameter of the wheel is also given, 40 centimeters, so its radius is 0.20 meter. What we are looking for is the car's average velocity, angular speed and angular displacement. For average velocity, so we use the basic formula, distance over the time interval, that is 1,500 meters over 60 seconds. So the average velocity or speed of the car is 25 meters per second. Letter B. From this formula, we solve for the angular speed, omega. So that is v over r. 25 meter per second divided by 0.2 meter equals 125 radians per second. Then we convert this to RPM, so it is equivalent to 1193.6 revolutions per minute. For letter C, from this formula we solve for angular displacement, so it is the distance d 1,500 meters, over the radius of the wheel, 0.2 meter. So it is 7,500 radians, then we convert this to revolution, so the wheel rotates 1193.6 revolutions, as it travels 1,500 meters. Do you have questions, guys? Kindly communicate with your teacher in Google Classroom. Let us give another sample problem. Problem number 6. In a typical Blu-ray player, the constant linear speed of the surface of the disc passing the fixed laser beam is about 5 meters per second. Letter A. Find the angular speed of the Blu-ray disc in revolutions per minute, when the information is being read from the innermost beginning of a high-density movie, in which the radius is 23 millimeters, and the outermost end of the movie, wherein the radius is 58 millimeters. Letter B. If the movie playing time is 135 minutes, how many revolutions does the disc make during that time? Letter C. Determine the angular acceleration of the disc over the 135-minute time interval. Letter D. Determine the magnitude of tangential acceleration, radial acceleration, and total acceleration of a point located on the rim of the disc. So imagine this is the disc data layer. The inner and the outer radii are 0.023 meter and 0.058 meter, respectively. This laser moves at a constant velocity of 5 meters per second from the inner radius, towards outer radius of the disc as it rotates, in order to read the data in which the movie is stored. The movie lasts 135 minutes, or 8,100 seconds. What we are going to solve are initial and final angular speeds, angular displacement, angular acceleration, tangential acceleration, radial acceleration, and total acceleration. For letter A, since the speed of the laser is constant, therefore the angular speed of the disc is increasing, as the laser moves away from the inner disc. From this formula, we solve for the angular speed. So the initial angular speed is v over the inner radius. Substituting the values, the initial angular speed of the disc is 217.4 radians per second. Converting to RPM, so it is equal to 2076 revolutions per minute. Then for the final angular speed, using the same formula, velocity over the outer radius, 5 divided by 0.058, so it is 86.2 radians per second. Converting this to RPM will give 823 revolutions per minute. Letter B, for angular displacement, since the disk slows down as it rotates, we assume its acceleration is constant, so we can use the formula, 1/2 of the sum of the initial and final angular speeds, multiplied by the plane time. Take note, we will use values of angular speeds in terms of radians per second, instead of RPM. Substituting the values, will give 1,108,080 radians. Then converting this to revolutions, therefore the disk rotates 176,356 revolutions during the plane time of the movie. For letter C, since the angular speed is changing, we can somehow determine the angular acceleration of the disk. So from this formula, it is expressed as the change in angular speed, divided by the plane time. The disk angular acceleration is -1.62 times 10 raised to -2 radians per second squared. Letter D, we are going to solve the tangential acceleration of the particle at the rim of the disk. So we just multiply the angular acceleration by the outer radius, so the tangential acceleration is -9.4 times 10 raised to -4 meter per second squared. Then next, for the centripetal or radial acceleration of this particle, we will use the formula, radius multiplied by the square of the final angular speed. So the centripetal acceleration is 431 meter per second squared. Lastly, for the total acceleration, we simply apply the Pythagorean theorem, square root of the sum of the square of centripetal and tangential acceleration. So since that the tangential acceleration is so small, we can say that the total acceleration is approximately equal to 431 meter per second. We see that this value is almost the same as centripetal acceleration of the disk.